Currently, astronauts on board the International Space Station have no way to manufacture tools or parts that are broken or need to be replaced. Instead, they must simply wait for the next supply flight to bring up replacements. This is both time and resource inefficient. To remedy this issue, NASA's HUNCH program is challenging high school students to develop a method to mold components in space. The mold is not restricted to any specific tool or part, but it must be cost-effective and usable in microgravity. The objective is to be able to use the 3D printer currently on board the ISS to create a mold with ABS plastic, which can then be used to cast tools and parts out of other materials like foaming RTV, fields metal, or epoxy. Our approach slightly modifies this framework to optimize efficiency and ease of use, with a 3D printed shell that is filled with the reinforcing material. Our product demonstrates the feasibility of this molding methodology, as our method serves as a launching pad to continue creating more tools and components.
So our objective was to create a methodology to fabricate replacement parts and tools on board the ISS that are stronger than parts 3D printed made out of only ABS plastic, and that are cheaper than sending up replacement parts on a supply flight that are made of metal. So the conventional solution to this is to create an entire injection mold setup with the 3D printer, and then actually create the inner object. There are many challenges with conventional injection molds. First of all, it's very hard to dispense the filler material in microgravity. You have to inject it very carefully and make sure that there are no air bubbles on the inside. If there are air bubbles, they ruin the structural integrity of the final object. This requires additional steps to make sure, either by centrifuging or other agitation, that the air bubbles are taken out. Extra steps that only add complexity and time.
The microgravity environment of the ISS leads to certain challenges when attempting to create molds. One of the most relevant is the behavior of liquids. Due to microgravity, liquids won't pour as they would on Earth, and therefore, to fill a mold require additional effort to force them down. Furthermore, there are certain safety regulations that must be followed in order to ensure the safety of those on board. These include limiting off-gassing and the elimination of small dust particles, including those created by the use of support material. The final constraint was due to resources. The 3D printer that we have access to at our school does not have the flexibility of other printers, and therefore cannot print as accurately as physically possible. The smallest thickness it can print is 30,000ths of an inch, nearly twice that of most printers, causing shell walls to be thicker than they otherwise would be.
As you can see, the mold filling that we used was hot glue, which did not end up successful as we had to cut the part in order to receive the actual socket, and the socket was not fully complete. Ultimately, this taught us that we cannot. Step 1 was modeled after a traditional in order to make an effective mold. Prototype 2 and 3 represent an untraditional method of molding where we take a shell and we fill it with a mold material. As you can see, prototype 2 and 3 were our first iterations of this concept, as we took a smaller version of a socket and we filled it with epoxy. However, ultimately we learned that in order to make this mold effective, we would have to widen the gap for epoxy to be filled, and that epoxy could not be supported on its own. Regarding Prototype 4 and 5, our group learned that rebar provided substantial support for structural integrity. Prototype 4 showed us that we could have a simple solution through paper clips through the same size socket that we have been using, and Prototype 5 showed us that we could scale up this socket in order to provide support through the use of machine bushings. Ultimately, the machine bushings provided a standard for the next prototypes that we would take.
At the preliminary design review, we were able to compare our solution to the solution of other teams across the Houston area. What we found actually validated our methodology because of a combination of versatility and simplicity. Our design is much simpler than those of the conventional method of having an injection mold because it requires less steps, which save the time of the astronauts. That's a concern that was brought up by a lot of NASA engineers. How much time does the flight crew actually have to spend behind this process? With our method, we minimize the time required. In addition, our method also is more versatile for different objects. With a conventional mold, you have to create an entirely new mold for every single object, which uses a lot of plastic. With this method, all you need is the shell of the object. You don't need to print any excess beyond the shell of the object that you want to create. What we found from the very first round of testing prototypes was that we actually needed to increase the size of the socket to make sure that we had enough tolerance that the shear force acting on the plastic wouldn't dig in and start slipping immediately. So the way that I addressed this was actually calculating the amount of difference between the radius of the socket on the flat edge and the radius of the socket at the corner. When you have a small nut, the hexagon, there's a very small difference between the radius at the flat edge and the radius at the corner. Because of that, it's really easy to strip the plastic and just end up with a spinning nut. So we upsized from a 3/8 inch socket to a 3/4 inch socket. That's the diameter from edge to edge of the nut that fits in the socket. With this, we were able to have around 1.5 millimeters of tolerance per corner, which is 0.03 inches. In our testing, what we found was that the failure point in the epoxy-filled sockets was the epoxy itself, where it cracked longitudinally, indicating a lack of tensile strength of the epoxy itself. It essentially split apart. With the woods metal, however, what we found was that the failure point of the socket was actually the interface of the wrench and the socket itself, so the square hole in the socket. Because that has a 3D printed edge, that edge, because it was only ½ inch squared, actually started shearing off before any damage happened to the material itself. And so the torque limits in our testing, the failure torque of these sockets was actually the failure torque of the shearing off of the plastic at the interface between the wrench and the socket, rather than the failure torque of the woods metal itself. Because of this, we also couldn't properly test the effect of the rebar, or the reinforcing material, on the woods metal socket. For example, the socket in which we had the washers in addition to the woods metal, there was a negligible difference in the torque failure point between that one and only the woods metal with no washers. And that was because they both failed at the plastic interface between the wrench and the socket, rather than the metal. The metal was still intact in both of them, even after the measured failure point torque. Our procedure for filling the socket with woods metal was, we had the woods metal in giant ingots, and so we actually had to double bag Ziploc the ingots, submerge them in hot water, wait for them to melt, use syringes to suck up the melted woods metal, and then inject that directly into the mold. So this was relatively hard to work with because of the physical unwieldiness of the metal ingots that we then had to melt before we actually put it into the destination. On board the ISS, this entire process is much simplified because this melting and repackaging in the syringes would be done on the ground before a supply flight. So crews on the ground can actually melt the metal and put it directly into the syringes and then fly up syringes. That way, astronauts can insert the pre-prepared syringes into the food warmer, melt the metal inside, take out the syringe, and then inject it directly into the socket.